Welcome to Maths with EJD. In this video, we continue to talk about numerical solutions to algebraic equations. In particular, we've been considering different methods for solving systems of linear equations. And we have seen those methods to be broadly classified into direct and iterative methods. So, in the last few videos, I think 3 or 4 videos here, we've talked about the direct methods like Gaussian elimination. Gaussian elimination. We've talked about LU decomposition. LU decomposition. And we talked about Cholesky decomposition too. Cholesky decomposition. Okay. I think that was about what we've talked about so far. Then we have, okay, I think they are fourth. There's still another one. Gaussian elimination, Cholesky decomposition. What else? What else? What else? Let me see. Okay, I mean, if I remember later, I can update that. Now, for the iterative methods, we have talked about. Yeah, from this video, I'll be talking about the iterative methods, starting with Jacobi method. So from Jacobi, I mean, this one is like stepwise. There are stepwise improvements in the methods. From Jacobi method, we move to Gauss-Seidel, Gauss-Seidel method, and then we move on to successive over relaxation. So far, like I said, we've done Gaussian elimination, LU decomposition taken care of, Cholesky decomposition also taken care of. Now we are going for Jacobi method, and then we'll move on to Gauss-Seidel method and SOR later. So one video for each one. So let's move on and talk about the Jacobi method, which is iterative in nature. Jacobi, Jacobi method for solving systems of linear equations. Now, when the first time I studied Jacobi method, I was looking the way it went. In fact, the whole iterative method thing. So the way it went at first, I was wondering what's the essence of the iterative methods if I can use the direct methods and get exact answers without having to waste my time. But after there's a fourth video after SOR, as far as iterative in fact, the last video for all the methods together. I'll be comparing all the methods and I'll be explaining the usefulness of these iterative techniques because they definitely have their place, which you may not appreciate right now because it will look like why are we wasting time? Okay. So the Jacobi method is an iterative numerical technique that solves a system of linear equations by updating. So now it's about updating each variable, updating each variable independently, independently using the previous, using the previous iterations values until convergence. Okay, so the general formula for each variable that is xi at iteration n plus 1 is given as, so you have it's given as xi n plus 1 equals 1 over AII into BI minus summation from J not equal to I of AIJ XJ to the nth power, like this. So where AII is the diagonal element of the coefficient matrix. You're going to see, you'll understand what that means as we move on. It is the diagonal element of the coefficient matrix. Then next you have AIJ, which are the off diagonal elements. Then you have BI, which is the constant term. That's like the right-hand side, the constant term. Then you have the XJN. You have the XJNs, and those are the previous iteration values. XJN are the previous iteration values. All right. So, having said that, can we just take the same example, the same problem we've been solving? So, like I said, we'll use all the methods to solve the same problem and see how they perform. So let's go. Let's take an example. Let me go black, right? Let's take an example. So again, solve x plus 2y plus 3z equals 9. Then 2x plus 5y plus 6z equals 18. Then 3x plus 6y plus 14z equals 30. Okay, so we go for the solution. So of course we've seen the general form, and so I'll just go straight. So first of all, we'll have x plus 2y plus 3z equals 9. So that's the same thing. Now, from what we've seen up there, right? This is xi something something equals something else. So it means for each, we are looking for x, y, and z. So you have to make them the subject of formula in terms. So for instance, this x now is going to be x equal to 9 minus 2y minus 3z. So 2y goes, 3z also goes to the other side, and the change sign. And from here, you can establish what the formula should be. So here now, you are going to have xn plus 1 equals 9 minus 2yn minus 3zn. Okay, so that's what we're going to use for x. Then we go for the next one. That one is from the first one. So we go for the second one, where we have 2x plus 5y plus 6z. So again, we have 2x plus 5y plus 6z equals 18. That implies that, you have, now y is the next thing you're going to look out for. So 5y equals 18 minus 2x minus 6z. Okay. And so that A11 we're talking about before is this 5 now. So y now is equal to 1 over 5 into 18 minus 2x minus 6z. Okay. So this is your A11 now. So this is your AIJ or something like that, which is the constant. So from here, we can also establish that yn plus 1 is equal to 1 over 5. So it's equal to 1 over 5 into 18 minus 2xn minus 6zn. Okay, so that is also settled. So we are going to use that in our iteration. So next we have the third equation, which is 3x plus 6y plus 14z equals 30. So that implies that now z is in turn, the focus is on z now. So 14z equals 30 minus 3x minus 6y. So that means z is equal to 1 over 14 into 30 minus 3x minus 6y. Okay. Now we can also establish a formula for that. So we have Zn plus 1 equals 1 over 14 into 30 minus 3xn minus 6yn. Okay, so we have the three things we need. Now, what you should also know is that, of course, there's going to be a tolerance limit and everything. So I can talk about that. Another thing is that you're going to have an initial condition. So so the initial condition will be given you, but most times if it's not given, you can just start from 0, 0, 0. So let the initial condition be x naught, y naught, z naught equals 0, 0, 0, and the convergence condition or convergence criteria, if you like, convergence criterion B, that it's the absolute value of the new value you get, xn plus 1, yn plus 1, zn plus 1, minus xn, yn, zn. So just like we've been doing before, so you compare the values and they have to be less than epsilon, which is than epsilon, right? Where epsilon is the tolerance limit, Okay, so but in this case, I won't worry so much about the tolerance limit because it can be quite a task. So, but at the end of after doing it manually, I'll just take maybe maximum 3 iterations and then I'll show you the Python code and then we'll move on from there. All right. So, so we have established all these things now. So we now need to so let's go for the first iteration. So first iteration. So going by the x, right, you need xn plus 1 equals, so imagine that n is 0, so that I can have y naught and z naught on the other side. So it means you're going to have x1 equals 9 minus 2y naught minus 3z naught. And interestingly, we already know this to be 0 each. So that implies that x1 is equal to 9 minus 2 into 0 minus 3 into 0. So that means x1, I think I want to highlight that because we need it in the subsequent place. So x1 is just equal to 9, okay? Because this is 0, 0 each. So x1 is 9. Then we move on to the next one. We need y1 now. So from what we have already, y1 is 1 over 5 into 18 minus 2xn minus 6zn. So it means that y1 is going to be 1 over 5 into 18 minus 2x naught minus 6z naught. Interestingly, these ones are zeros too. So this 1 over 5 into 18 minus 2 0 minus 6 0. So you see all of this will cancel out. So at the end of the day, you have y1 to be equal to 18 over 5. Well, 18 over 5 is the same as 3.6. I like to use fraction because it preserves the value, but you can feel free to use decimal. Okay, so we have x1, we have y1 now. So we go for z1. So Z1 is equal to, so from what we have up there, Z1 is 1 over 14 into 30 minus 3xn. So this will just be Z1 equals 1 over 14 into 30 minus 3x naught minus 6y naught. So Z1 now is 1 over 14 into 30 minus 3x naught minus 6y naught. And that is 1 over 14 into 30 minus 3 into 0 minus 6 into 0, like that. So this cancel out because that's 0 each, and that ends up giving us, so it means that Z1 is equal to 30 over 14, and that is 15 over 7. 15 over 7 is the same thing as 2.1429. So you can use the decimal, you can use the fraction. Like I said, I prefer the fraction. So we have got our first iteration. We've got x1, y1, z1. So that ends the first iteration. So we go now for the second iteration. Of course, I mean, like I said, I'm not going to bother about the tolerance limit because it can be quite a task. And of course, I already know that this requires compared to the direct method, this requires quite a number of iterations to get to what you want. Of course, we already know from what we've been doing, right, that x1, if you solve this equation, this system, x1 is 7.2, I think, and then y1 is 0, and z1 is I think 0.6. So I mean, this is not even looking close to it. So I'm not even going to bother to do the iteration thing. I mean, to do the convergence criteria thing. So not to worry. So I'm just going to do 3 iterations, show you the Python code, and from there you're going to see the number of iterations required to make it converge to the required result. So we go for the second iteration. So for the second iteration now, we just update. So instead of x1 equals 9 minus 2y naught minus 3z naught, it's now going to be something like x2 equals 9 minus 2y1 minus 3z1. That's what we are going to have next. And we keep updating like that. So I go for the second iteration where we now have x2 to be equal to 9 minus 2y1 minus 3z1. And that is 9 minus 2. So don't forget the y1 we got was 18 over 5. Like I told you, I like fraction. 18 over 5. You can put 3.6. You're going to get almost the same thing. And then minus 3 into z1. Z1 is 2.1429 or 15 over 7. I prefer 15 over 7. And if you work all of that out, so it tells you that x2 is going to be equal to minus 108 over 7, which is minus 15.4286. So feel free to use, I put fraction and decimal, so you can use anyone that works best for you. Then I go for y2. Y2 now is 1 over 5 into 18 minus 2y1 minus 18 minus 2y1, or rather 18 minus 2x1, sorry. Yeah, 18 minus 2x1 minus 6z1. 18 minus 2x1 minus 6z1. That is what y2 is going to be. So, and that is 1 over 5 into 18 minus 2. X1 that we had before, right, is x1 is 9, right? X1 up here is 9, yeah. Then minus 6z1. So z1 is 15 over 7, okay. So if you do all that together, you discover that y2, so if you punch your calculator for all of this, you see that y2 will be minus 18 over 7, okay, minus 18 over 7. That is equal to minus 2.5714. So we have y2 right there. Have y2. Then I go again for z2. So z2, if you look at the first one, so z2 will be 1 over 14 into 30 minus 3x1 minus 6y1. So z2, okay, z2 is 1 over 14 into 30 minus 3x1 minus 6y1. So that is 1 over 14 into 30 minus 3. X1 is 9 and 6 into y1. Y1 is 18 over 5 or 3.6. So that's 18 over 5. Okay. So, I mean, punch your calculator straight for that and you get, okay. Let me be consistent with my style. So Z2 now is minus 93 over 70, which is the same thing as minus 1.3286. Okay. Minus 1.3286. And that is the second iteration completed. Now we've got x2, y2, z2. So I'm going for the third iteration now. So we have the third iteration. So I'm going to stop on the third iteration because we can continue because we know the answer, right? But I mean, even if you don't know, you have to keep going and keep checking more. The Python code is going to complete it, so no problem. So now x3 is just going to be 9 minus 2y2 minus 3z2. and that is 9 minus 2 into, what is y2? Y2 is minus 18 over 7. Minus 18 over 7. Then minus 3 into Z2. Z2 is minus 93 over 70. Minus 93 over 70. So punch your calculator. You need to master your calculator in this case. Extremely important. So minus 93 over 70. By the time you're done doing that, x3 is going to give you 1269 all over 70. And that is the same thing as 18.1286. 18.1286. So that is x3. And then we go for y3. So y3 is equal to that's 1 over 5, right? 1 over 5 into 18 minus 2x2 minus 6z2. That is 1 over 5 into 18 minus 2. What is x2? X2 is minus 108 over 7. Minus 108 over 7 minus 6z2. Z2 is minus 93 over 70. Z2 is minus 93 over 70, minus 93 over 70, like that. And then at the end of the day, we have y3. If you punch your calculator right, you're going to get y3 to be 1989 over 175. And that is the same thing as 11.3657. Okay. So that's your y3 right there. And then we go for z3, which completes the third iteration. Z3 is 1 over 14 into 30 minus 3x2 minus 6y2. And that is 1 over 14 into 30 minus 3x2. Don't forget, x2 is minus 108 over 7. Or you can use the decimal, like I said, 108 over 7. Then 6y2. That is minus 6. Y2 is minus 18 over 7. Okay. Punch your calculator right, and Z3 is going to be the same thing as 321 over 49. And that is the same as 6.5510. And that is the third iteration. So we have got x3, y3, z3. So at this point, I mean, we could keep going, but you can clearly see that we have not got the exact solution based on what we have done previously. We know is the exact solution has been okay. I think I should still remember. Exact solution is x equals I think 7.2. That's 36 over 5, yeah? X is 7.2, Y is 0, and Z, I think, is 0.6. That's 3 over 5. That's the exact solution. So you can see that the after third iteration, the result, they are still very far from what we currently have. Okay? But then, not to worry, we'll complete the rest with Python. So follow me and see what Python tells us about this. Now, just like I said, these iterative methods can be quite they can be quite problematic, especially if it's not suitable for the particular problem you're solving. So, but of course, we are going to see all the possibilities and work around them. Okay, desktop maths with EJD, numerical analysis. And then I'm talking about, yeah, numerical solutions of algebraic equations. Yeah. So, okay, before now I didn't show all this Gaussian elimination and everything, but this is the first one is for Gaussian elimination. And in one blow, it just tells you 7.20 and 0.6. We have all of those in place. LU decomposition, with all the long process, we have the same thing. Then Koleski decomposition, which was the last video I did before now, also gives us very roughly the same thing. Then now this is Jacobi. Now, okay, I mean, if you follow, somehow I couldn't put the code in this in Python on YouTube. I don't know, because of the angled brackets. They are not allowed in the description box. But if you can follow me on Facebook, I have all the codes. Check at the bottom of the caption. You are going to find all the code for each problem there. Okay, so this is for Jacobi, which we are currently on. So if I click this now, I mean, it just gives us an answer which is pretty far. Like, so it looks like the answer is diverging. So, and it doesn't even converge because maximum iteration has been reached. If you look at the setting, the maximum iteration set is 100. So it has reached the maximum iteration and it is giving us very totally different result from the 7.2, 0, and 0.6 that we're expecting. So it means that Jacobi method does not work very well with this particular method, right? Doesn't really work too well. So that's what we have. Imagine if I even double the maximum iteration and run it, it's still going to have the same effect. It has run 200 iterations and it's still, so you can see the answer is converging very fast. So the answer is not looking well as far as Jacobi is concerned. So that's how far this has been. So watch out for the next video, which is on Gauss-Seidel. Gauss-Seidel is actually an improvement on Jacobi method. So you don't want to miss out on that. So if you have not subscribed, if you have subscribed to the channel, thank you very much for doing that. If you have not, you'll be missing out. So don't don't miss out at all. Subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. And comment, let me know how helpful this video is to you. And also let me know if there's a topic you want me to teach and a problem to solve. I might be able to find time in the future to deal with all of those. And then, of course, like and share so that more people can have access to this great content. Till I come your way again, keep enjoying maths. Bye.